Hello? How's it going now?
Good now.
Can you see the shared screen now?
Yeah.
Okay, is this better?
Yeah.
Okay. The program works, but I never understand why it works at some times and it does not work at other times.
I don't know either.
All right, let me just send an email to everyone else and remind them that we are meeting now.
Okay.
And then we will start because it's getting late on my end. And then it's 605
633
3246.
Yeah.
Okay, perfect. Okay. So what I want to do today is talk about theory of games and talk a little bit about how to attack and prove results.
Okay.
And so for the most part, this is going to be non-calculus based. It's going to use something that goes no further really than 10th grade math.
10th grade math.
It's going to be looking at things the right way. All right. And so I want to start off with a proof of the irrationality of square root of 2. We don't really need this directly in what we're doing, but it's good math to see, and it's going to help us think about things elementarily, and it's going to help us think about things geometrically. So the standard proof goes as follows. Assume the square root of 2 is rational, so we can write it as a over b, where a and b are two integers. Without loss of generality, we can assume that b is the smallest denominator among all numbers that have a ratio of equal to square root of 2. And so we get 2b squared is a squared. So a squared has to be even. So with a little bit of work, you see that a has to be even. Because if a was odd, odd times odd is odd. So a must be able to be written as twice times m for some integer m. So we get 2b squared is 4m squared, so b squared is 2m squared, so b is 2n, so b is even. So we get the square root of 2 is a over b, is also 2m over 2n, which is the same as m over n, and now we have a smaller denominator than b. And that contradicts minimality of n, and that completes the proof.
Okay.
So the goal is to find similar stuff. And so we want to try to find similar stuff. Just 1 second.
Oh.
Okay, any questions on the standard proof?
No. No.
Okay, so now here's a geometric proof. And this goes back to Tenenbaum in the 1950s. Imagine the square root of 2 equals a over b, where b is minimal weight. Just got an email, let me see if that's one of them. Nope. Okay. So imagine we can write the square root of 2 as a over b, where b is minimal. So b is going to be the smallest of all the things that work. So a lot of these proofs go by proof by contradiction. So have you seen proofs by contradiction?
No. No, I don't think so.
Okay, so the way proofs by contradiction work is you assume something is true, and then you show that that leads to a contradiction. It leads to a false statement. And so if you've only made one assumption, then your one assumption must be false.
Okay.
So both of these are going to be proofs by contradiction. And a lot of the reason for doing this is to show all of you new proof methods. So we're assuming the square root of 2 is a over b, where b is the smallest of all possibles. So maybe there's more than one way to write the square root of 2 as a rational number. We can sort all of them, and we can look at the one that has the smallest denominator. And so in our picture now, the upper left and the bottom right are squares that are b by b. And because we're assuming square root of 2 is a over b, that's the same as 2b squared is a squared. Well, the big square is a by a. So what this is saying is those two squares have the same area as the big square. And those two squares cover everything once, except for the center, which they cover twice. And except for the corners, which they don't count at all. So the parts that they miss, their area must be the same as the area that was double counted. Does that seem reasonable?
Yeah. Yeah.
So now we get, when you do a little bit of work, you see that the small squares that are missed are a minus b by a minus b. And the largest square that's missed is 2a minus b by 2a, I'm sorry, 2b minus a by 2b minus a. So it's a good homework problem is try to confirm those dimensions. And we then get that the double counted area has to equal the area of the two parts that are missing. So you get 2b minus a squared is twice a minus b squared. So you get a new formula for the square root of 2. It's now 2b minus a over a minus b. And all you have to do is do a little bit of work, and you see that the new denominator, a minus b, is smaller than b. And that contradicts the minimality of our b. It contradicts the fact that we assumed we were looking at the smallest size denominator among all the things that were good. So this is proof by contradiction. This is a major, major argument that we have. Okay, and then I've written a paper on this with one of my students, and there's a lot you can do on this. So if you're interested, you can always email me. I'm happy to share the paper. But again, it's coming down to, can you be clever? And how do we make these arguments rigorous? Okay, so let's start moving to some other games. And the goal is to get to the Fibonacci game tonight. And I've got some problems that I can give you and the other students to look at. So let's first talk about tic-tac-toe. So how many opening moves are there in tic-tac-toe? So since it's only you tonight right now, you get every question. Sorry about that. Can you hear me?
Yeah.
Okay. So how many opening moves are there in tic-tac-toe?
8.
Why 8?
Because there is a square inside, and there's 8 open moves outside.
Well, can't you go in any square? Shouldn't there be 9 opening moves? But shouldn't there be 9 opening moves?
Why should it be 9?
Getting 8 opening moves. So you have to speak up because it's just you tonight, okay?
Okay.
So why are you only getting 8 opening moves?
Because the square is not included in it.
What square is not included?
Like the square in the center.
You can go there as an opening move.
Oh.
In fact, the center is often considered the best opening move.
Can you explain what is opening move?
When you start on your first turn, how many squares can you move into? You have to choose a square. How many choices do you have for your first move?
9.
I'm sorry?
9 squares.
There's 9 opening moves, right?
Yeah.
And then how many responses are there? How many moves does player 2 have?
8.
8. So it looks like there's 72 possible pairs of opening moves. I claim there's much less. I claim the 4 corners really are the same. You really can't distinguish an opening move in one of the 4 corners. That you can just rotate or reflect the board. Do you agree with that?
Yeah. Yeah.
What else is going to be the same?
The other 4.
What's the other 4? There's 5 squares left. What's the other 4?
And the top, bottom.
Yeah, the 4 middles will all be the same. And in the center. So really, up to symmetry, there's only 3 opening moves. And when we get to your games, we want to find efficient ways to analyze things. So let's look at the 3 possible first moves. You can go in the upper left, you can go in the top middle, or you can go in the center. Now, again, if you go in the upper left, you could have gone in one of the other corners, but those moves are all equivalent. So let's just assume we went in the upper left. Same for the other 2 places. And now let's look at responses. So if you go in the center, it's clear that if somebody responds in the middle, any of the 4 middles is equivalent. If you go in the middle, so we're now looking in the, are you able to see my hand when I move the hand onto the screen?
Yeah. Yeah.
Okay. So when I go here, these 2 moves are the same, but nothing else is equivalent to those. And similarly, if I go in the upper left corner, the 2 moves mark are equivalent, but nothing else is equivalent to them. And you can go through and you can see what possible opening moves you have and responses. And you can see that in the first case, there's 5 equivalent classes of responses. In the second, there's also 5, and in the third, there's only 2. So really, there's only 12 pairs of opening moves. You know, player 1 and player 2 responding. That's far less than 9 times 8 is 72. And the whole goal in a lot of the analysis is to force a player to walk down a specific path so that their moves are forced. So if I'm going in tic-tac-toe, let's go back over here. If I go in the center and you go in the middle over here, okay? If I then go in the corner down here, I'm threatening 3 in a row. You have to go here to stop me now. That makes the analysis a lot easier because your move is now forced on you. And then I can go in the bottom corner here and threaten 3 in a row that way, diagonally, or 3 in a row that way, and you can't block both. So in terms of analyzing games, it's much easier if you can do things that force a player to respond a certain way. It cuts down on possibilities. So, a couple of questions you could ask about tic-tac-toe, and we'll try to generalize these later on to the Fibonacci's, is does either player have a winning strategy? And it turns out if both sides are playing intelligently, every game of tic-tac-toe will be a draw. You could ask what happens if people play randomly. What if a computer plays and just randomly goes and takes an available spot? What's the probability player 1 wins now? Or you could do a slightly more intelligent computer. The computer first looks and sees if the other person is threatening 3 in a row or if it can get 3 in a row. If it sees one of those options, it does it, and if not, it just chooses a point randomly. So that would be a slightly more intelligent computer. The last one is, can we make the game of tic-tac-toe interesting? And so here are 4 different versions of tic-tac-toe that are now interesting. So the first one is called tic-tac-toe and tic-tac-toe. I think it might sometimes be called super tic-tac-toe. Have you ever seen this game?
No.
Okay.
No.
So the way it works is the following. Let's say you start off on your turn and you go over here in the upper right spot in the middle board, okay?
Okay.
Because you went in the upper right, that means I have to go in one of the squares in the upper right board. Let's say I choose to go here. Now that means you have to go somewhere in the center middle. So center, left side, middle. So now if you go over here, that means I get to go up here again. So I'll choose the center. You've got to go somewhere in the center board. Let's say you go here. I've got to go down here now. I go in the center. Well, that's a really stupid move because you'll go here and you'll get 3 in a row. So sometimes people play that as soon as you get 1 3 in a row, you win. Other people play you have to get 3 in a row on the big tic-tac-toe board. And if you get to a point where you need to go on a board, but that board is already filled up, then frequently the rule is you get to choose which board to go to. So the question is, does this tic-tac-toe have a winning strategy? So not so easy to analyze this one. Another one is bidding tic-tac-toe. We each start off with a certain amount of money, and we bid for moves. And whoever bids the most gets the move. Then, a natural question is, how much should you bid for the opening move? Is there an advantage in tic-tac-toe to going first? What do you think? Is there an advantage to going first?
Choose the center one.
Choose the what?
Choose the one in the center.
Yeah, choose the one in the center. There's a huge advantage to going first. And if you choose the center one, that's going to be involved in a lot of tic-tac-toe possibilities. So let's say we both start off with $1,000. Player 1 bids 300, player 2 bids 700. So player 2 bid more, so player 2 gets the move. And then player 1 gets the $700. Let's say now player 1 has $1,700, player 2 has $300. Player 1 bets 99, and player 2 bets 100. So now player 1 has $1,800. They can actually get the next 3 moves. They bid $201, then $402, then $804. And so in something like this, you're actually willing to lose a few moves if you can then get 3 moves in a row later in the game. And so the question is, what is a good opening bid? Or a better way of phrasing it, what would be a bad opening bid? Can you tell me a bad amount to bid of your $1,000 for the opening move? So can you give me a bad opening move, a bad opening bid? We just saw over here that they bid too much money after the first 2 moves, and I was able to get 3 moves in a row, right?
Yeah.
So you don't want to bid too much on the first move. Can you give me an amount that's clearly too much to bid? It's okay if it's not the best amount, but just give me some amount that's clearly too much to bid for the opening move. If you start off with 1,000 and I have 1,000.
900.
900. Yeah, we know over here that after when player 1 had $1,800, they were able to get the next 3 moves. So anything 800 or more is clearly too much. $1,000 is clearly too much, because if you bet $1,000, you'll have nothing left. So the question is, what's the best we can do? So over here, imagine player 2 bids X dollars and wins. So we start off with each person having $1,000, then player 1 would have 1,000 plus X, and player 2 would have 1,000 minus X. To just make life simple, I'm not going to really worry so much about what happens if there's a tie. I'll assume that maybe one of the players wins it. So now, player one bids 1,000 minus X and just barely wins. So we're going to say player one wins any tie, just to make things easier. If not, you have to make sure that player one has just one more dollar available. And the reason is, player two is trying as hard as possible to prevent player one from getting a move. So we bet 1,000 minus X and win. So player one now goes to 2X. Player two is 2,000 minus 2X. So player one bids 2,000 minus 2X and just barely wins. Now they have 4X minus 2,000 to 4,000 minus 4X. Happens one more time. They bid 4,000 minus 4X and just barely win. And so now we can just analyze. We need 4X minus 2,000 to be greater than or equal to 4,000 minus 4X. We have to be able to beat their bid. So we get X is greater than or equal to 750. So if you bid 750 or more for the first move, we can prove to you that that's too much. We haven't proved what is the right opening bid yet. What's a good amount? And this is just going through those calculations again, but actually just using numbers to make it a little bit clearer. Okay. So I'm going to show you a bunch of different games leading up to the Zeckendorf game. And the purpose of this is to just show you some good math and get you a little bit comfortable with analyzing games. So any questions on what we've done up till now?
Yeah.
Okay.
Yeah.
So the first is the rectangle game. So consider an n by n board, and on each turn, we're going to alternate turns. You break any piece along one horizontal or one vertical, and the last one to break wins. Does someone have a winning strategy, a way to guarantee that they win, and what is it? So for example, on my opening move, maybe I come all the way down here. And then on your turn, you choose to cut over here. You have to stop cutting as soon as you get to a cut line, okay?
Okay.
You can't just cut part of the way. You have to go all the way until you hit a cut line. So maybe on my turn, I come in like this. Maybe on your turn, you come all the way down like this. And on my turn, maybe I'll come over like that. And then you maybe come down like that. And so on and so on. So one way to try to figure out what's going on is to gather data. Play on lots of different boards. Okay?
Yeah.
And if you do this, it's going to come out that if the board has an even number of squares, player one always wins. If it has an odd number of squares, player two always wins. So when you look at this, is it clear just by looking at this that that's what's going on? I don't think that's immediately clear. So what I want to show you is another way to look at this game. So let's see what happens. So we're going to use what's called a monovariant, and this is something that will emerge when we get to the Fibonacci games. So it's a quantity that moves in only one direction. So if I look at somebody's age, do you think age is a monovariant? Do you think it only moves in one direction?
Yeah. No.
Yeah, do you think you're going to wake up and be younger?
No.
No. What about somebody's weight?
It's not.
Yeah, weight could go up and down. What about temperature?
Yeah.
Up and down.
Yeah.
So the idea is we want to associate a monovariant to the rectangle game. And the monovariant is going to be the number of pieces. So in move 0, there's one piece, the whole big board, okay?
Okay.
After the first move, we now have, we can imagine now we have 2 blocks. So after one move, there are 2 pieces. Now we came down over the middle. After 2 moves, there are 3 pieces. After 3 moves, there are 4 pieces. After 4 moves, there are 5 pieces. After 5, oops. Oh, there's a typo. This should be 6 pieces here, not 5.
6 pieces.
Right. So the number of pieces is always one more than the number of moves. So every time you have a move, one way to view this problem is you're breaking it up into small and smaller blocks. You increase the number of pieces by 1. And so if the board is m by n, you have m times n pieces. It takes mn minus 1 moves. If mn is even, then you're going to end on player 1. Otherwise, you end on player 2. So this is the power of looking at a monovariant. We're going to look at another thing called the zombie game. And this is going to be another game where the monovariant is going to help us figure out what's going on. All right, we've talked about the law of the hammer before. So here's how it works. If you share walls with neighbors, you'll share walls with neighbors, and if 2 or more of your neighbors are infected, you become infected, and once you're infected, you're always infected. So here is an initial configuration. And if you look at this, 2 squares, this one here and this one here, both share 2 walls with neighbors that are infected, so they become infected. And initially, nothing else shares 2 walls, so they become infected. Are there any other cells that become infected now? Well, yes, this one over here will become infected, and this one over here will become infected, right?
Yeah.
And this corner one and the one down here will become infected. Are there anything else now that share 2 cells, 2 walls with 2 infected cells?
No. No.
No. So the virus stops over here. It doesn't go any further. So the question is going to be, what's the least number of infected cells we need to guarantee that everybody becomes infected? So rather than trying to find the least, let's just find a very simple pattern that ensures that eventually everybody's infected. Can you give me a simple pattern? So it's okay if you have more cells infected than the minimum. Can you give me a set of infections that guarantees that everybody will be infected at some point?
Can I draw on a screen?
I don't think you can try to draw on my screen.
Okay, because I tried last time and it works.
Okay, well, but you can just tell me there's a very simple solution that ensures that everybody gets infected. What's the simple solution? Be as crude as you can. It's okay if you infect more cells than you need.
We can have 2 squares, and they're like from this one and this one. Wait.
Well, but no, be cruder. You're being too clever right now. Okay. What's the simplest configuration that guarantees everybody's infected at some point? The simplest configuration. So you need to give me a configuration that's going to ensure that eventually everybody's infected. There's a very simple solution that makes sure that everybody's infected. You infect everybody. Okay?
Yes.
This is what you need to get into your mind as to how to get to simple solutions like this. I want extreme cases. If I infect everybody initially, then I'm pretty sure that eventually everybody gets infected. I force it to start that way. Then we can try to do better. Can you think of a pattern that's a little bit better than infect everybody, but will still ensure that everybody gets infected?
You can clear half of them.
Yeah.
One next to each other.
Right, you could do a checkerboard pattern. And so that's a 50% savings. So that's pretty good. Now, if you think about it, if you infect everybody, that's n squared. If you infect every other person, that's 1/2 n squared. It's a 50% savings, but you're still infecting on the order of n squared. So can you infect far fewer people than a 1/2 n squared and still guarantee that eventually everybody's infected? Any thoughts? I think you started to draw it before. What's a good configuration to do the infection? What are your thoughts? So you got to give me something. What were you doing before?
This.
So why don't you, yeah, if you just infect the main diagonal, then on the next turn, you get the diagonal above and below. And then the next turn, you just keep getting more and more diagonals, and it pushes out and you get everybody. So if you infect just the main diagonal, you will get everybody. That's infecting n squares out of n squared. Is it possible to get everybody if you only infect n minus 1? And the answer is no. And the proof uses another monovariant. So it's a quantity that only moves in one direction. And so the monovariant is going to be the perimeter of the infection. So imagine you only have 2 neighbors that are infected. So you're going to become this new infected cell here. These 2 walls here were part of the perimeter of the infection. Now they're internal walls, so they're no longer part of the perimeter, but you gain these 2 walls here and here. So the net effect is the perimeter is not changed. If I was like this, the perimeter wouldn't be changed either. Now, if I'm like this, I have initially 3 walls are part of my perimeter. When I now become infected, I lose those 3 to internal walls and I only gain 1 here. So the perimeter decreases by 2. And in this case, the perimeter decreases by 4. So we see that for this problem, the perimeter never goes up as the infection propagates. If we have n minus 1 cells infected, the maximum area we can get, the maximum perimeter we can get is if they share nothing in common. So it'd be 4n minus 4. But the perimeter is 4n. And so since the perimeter is never going up and it starts less than 4n, it's 4n minus 4, there's no way we can infect everybody. So there's a lot to think about here for this problem. It's truly wonderful. The hard part is finding the right thing to associate. But when we find it, we're in great shape. All right. So the next one is the I Love Rectangles game. All right. Here's the challenge. Oops, I'm not sure why it's displaying poorly like this. You have exactly 1 n by n squared for each end. So you have a 1 by 1, a 2 by 2, a 3 by 3, a 4 by 4, a 5 by 5, and so on and so on and so on, okay?
Okay.
On your turn, you choose one of the squares and you put it down on your table. And then on your next turn, you put another square down on the table, and you want to make sure that you always have a rectangle. So if I start off by putting down a 4 by 4 square, I no longer have any 4 by 4 squares. Is it possible to put down another square next to it and keep it as a rectangle? No, because if I put down a 4 by 4 square, to have a rectangle, I need to put down something that has a side of 4. So this game is pretty boring, right? You can only put down one tile and keep things as a rectangle. Do you agree?
Yeah.
So what we're going to do is I'm going to give you two 1x1 pieces. So what's your first move now? What square do you put down initially? So what square do you put down first? Do you put down a 1x1? Do you put down a 2x2, a 3x3? What should we put down first?
2x2.
We don't have it. Okay. So if we put down a 2x2, is there anything we could put down next to the 2x2 on our next turn? We don't have anything else that has 2 for a side length. So we can't start off by putting down a 2x2. So you have to try again. I'm sorry?
1x1 first.
Yeah, put down a 1x1. What do we put down next to the 1x1?
Another 1x1.
Another 1x1. So now we have a 1x2 rectangle. What can we put down now?
2x2.
Right, and you can either put it up or down. I'm going to choose to put it down. Now what could we put next to it?
3x3.
3x3. What can we put down next?
5x5.
5x5. What do you notice? What numbers are these? 1, 1, 2, 3, 5.
Fibonacci number.
Yeah, Fibonacci numbers. What would come down next?
8.
8. So it's going to tile the plane. So I might have shown you this picture before. This is from a Fibonacci conference I went to. You can see the Fibonacci spiral that I've made on a Rubik's Cube. This is the Fibonacci spiral. So by giving you that extra 1x1 square, we can now put down infinitely many tiles and make it ever expanding, filling up the unit plane. All right. I'm going to skip the triangle game for now because it's just us tonight. And I'm going to go to Zeckendorf games. All right. So we're going to write the Fibonacci's as 1, 2, 3, 5. We're not going to have the double ones. And the reason is we want Zeckendorf's theorem. Every positive integer can be written uniquely as a sum of one or more non-consecutive Fibonacci's. So we've talked about this. We've talked about how to use the greedy algorithm. If I do 2018, I throw away the largest Fibonacci number I can, look at the difference, throw the largest I can away, and keep going. All right. It turns out that this is an equivalent definition for the Fibonacci's. The Fibonacci's are the unique sequence such that every integer can be written uniquely as the sum of non-adjacent terms. So if I start off with 1, if I want to get 2, I have to add 2. Can I add 1 and 2 to get 3? Would that be legal with my rule that I can't have repeats and I can't have adjacent things?
Yeah.
No, so I have to add 3. Can I get 4? So can I get 4 using these numbers and not having 2 things that are adjacent?
One plus 3.
I'm sorry?
1 plus 3.
1 plus 3. So I don't need to write down 4. What about 5? Can I get 5?
No.
No, so I have to add 5. Can I get 6?
Yes. 1 plus 5.
How do I get 6?
1 plus 5.
1 plus 5. Can I get 7?
Yes. 2 plus 5.
2 plus 5. Can I get 8?
No.
No. So you can see this is very similar to what we did with the Fibonacci quilt. Can I get the number 9?
Yeah.
Yep, that's 8 plus 1. Can I get 10?
2 plus 8.
2. Can I get 11?
3 plus 8.
Okay, can I get 12?
1 plus 3 plus 8.
Excellent. Can I get 13?
No.
No. As you see, 13 needs to be added, and so on and so on. So it turns out these are two equivalent definitions. Right. Now, a big thing is called sum and minimality. So I gave you two different decompositions of 18. One is the Zekudov decomposition, 13 plus 5. Another is 13 plus 3 plus 2. And that has more terms. And it turns out that the Zekudov decomposition is always minimal. There might be another decomposition that has the same number of terms, but nothing is going to have fewer terms. So how would you write a legal decomposition for 16?
13 plus 3.
13 plus 3. It's also 8 plus 8. 8 plus 8 is not a legal decomposition, but it is a sum of Fibonacci numbers. And that shows you that it's possible to have the same number of terms. So you could ask, what other recurrence relations have minimal summons? I'm going to skip this for now. It turns out that you can associate a monovariant. I'm going to skip how you do the monovariant, but I just want you to see right now that there is a way to do something very similar to what we did last time. So we're going to almost surely do a lot of this material again with the other people, so this is going to be a first pass. But by using monovariants, we can show that the Zekudov decomposition can't be beat. There's nothing that has fewer summons. So I'm going to teach you now the Fibonacci game. So I created this game a few years ago. So there's two players, they alternate, the last one to move wins. And so you start off with the bins that are going to be the Fibonacci numbers. So F1 is 1, F2 is 2, F3 is 3, F4 is 5, and so on and so on. And we start off with n pieces on bin 1, and all the other bins are empty. And on your turn, you can basically do one of the following two things. If you have 2 pieces on a bin, you can remove and put a piece on k plus 1 and one at k minus 2. So this is the same as 8 plus 8 is 13 plus 3. We took 2 things on the bin, on the bin F5, the 2 8s, and replaced it with something on bin 6 and something on bin 3. Okay?
Okay.
We have to be a little bit careful. If k equals 1, if we have 2 things on bin 1, then we replace it as just a 2, and it's really a 2 plus a 0, but we don't really keep track of the zeros. Okay? The other thing is if we have something on 2 consecutive bins, we can remove each of those and put something on the next one. So if we have something on the 8 and something on the 5, we can remove those and just put something on the 13. So there's a couple of questions you can ask. Does the game end? And if so, how long does it take? For each end, who has the winning strategy? And what is the winning strategy? And so we can answer some of these questions, but not all. And I'm hoping that you and your friends will be able to answer some of these ones that are open. So let's look at a game very slowly, very carefully. So we're going to start off with n equals 10. So here's my first 5 bins. Okay, and I have 10 pieces on bin 1. Okay?
Okay.
I notice that 10 times 1 plus 0 times 2 plus 0 times 3 equals 10. I don't have to worry about the bin F6, which is 13, because there's never a chance that if I start off with 10, I could have anything involving that number. So there's only one opening move. I have to take 2 things on 1 and give myself something on a 2. Do you agree that that's the only move? I have two types of moves. I can combine two things in adjacent bins, or I can take a double and break up a double. We don't have two things in adjacent bins. We only have one bin. So do you agree that this is the only possible move?
Yeah.
So do you agree that this is the only possible opening move? You have to say yes or no.
Yeah. Yes.
Okay. Okay. You got to answer so I know if you understand things, okay?
Okay.
So now we have, we start off with 10 things here. We take two things here, so we have 8 here and 1 here, okay? Notice 8 times 1 plus 1 times 2 plus 0 times 3 still adds up to 10. So the weighted sum is always going to be 10. So I say on my next move, I'm going to take two things on 1 and give myself another thing on 2. What else could I have done? So I chose to break up another double. What else could we have done?
Can you put something on the 3?
I'm sorry, what could we have done?
Can you put something on the 3?
Yeah, we could have taken something on bin 1 and something on bin 2 and made something on bin 3. That would have been a perfectly fine move as well. So now we chose to do 2 more on bin 1 and move it to bin 2. Now we have 6 on bin 1, 2 on bin 2. Notice the weighted sum is still 10. And now I'm saying, let's take the double on F2 and split that into an F3 plus an F1. So 2 plus 2 is 4 is the same as 3 plus 1. What else could we have done rather than splitting the double on 2? So I chose to take the double, the two things on 2 and split them. What else could we have done?
Move something from 1.
We could have taken the double on 1 and split that. Or what else could we have done? We could have taken something from bin 1 and something from bin 2 and made something on bin 3, correct?
Yeah. Yeah.
Okay. So now we chose to split the double on 2. So we have 7 things on bin 1 and 1 thing on bin 3. I claim that the only move we can do now is to split a double on 1 because we don't have 2 adjacent bins. So we have to take 2 things on bin 1 and make something on bin 2. Notice 5 times 1 plus 1 times 2 plus 1 times 3 still adds up to 10. So now I'm saying, let's do F2 plus F3 is F4. What other moves could we have done? I'm choosing to do F2 plus F3 is F4. What else could we have done? So one move was to combine bins 2 and 3. What else could we have done?
Can we have 2 F1 and
Good, we could have taken a double on F1 and replaced it with something on F2. And there's one more move we could have done. Excellent. So we had adjacent things here. We combined 2 and 3 to get 4. What else could we have done?
can we take double F2?
Well, we don't have F2 as doubled, right?
Oh yeah, we just have 1.
We just have 1. So we have F1 that's doubled. We could have split that up as you remarked, which was good. what else could we do? We combined a 2 and a 3 because they were adjacent, right?
Yeah.
We don't have any other double, so it's got to be an adjacent. What's the only other adjacent we have?
Take 5 F1.
Yeah, we've got F1 and F2. We could take one of the ones here and one of the ones here and combine them. So now I chose to combine the 2 and the 3 to get a 5. The only thing we can do here is we have to split up the double we have on F1. And now on this one, what moves could we do? We could take the double on F1 and make it a 2. What else could we do?
Take 1 from F1 and take 1 from F2.
Okay, you've got to speak up clearly. It's tough to hear with the connection. What else could we do?
Take 1 from F1 and 1 from F2.
Excellent. Excellent. And we could have done that. I chose not to. Now on this turn, I can take 1 from F1 and 1 from F2 and make an F3, or I could split up the F2. Now on this one, I could take an F3 and an F4 and make an F5. What else could we have done? So I chose to combine a F3 and an F4 to make an F5. What else could I have done?
Combine F2 and F3.
Excellent. And so I combined F3 and F4 to make an F5. No moves are left, right? There's nothing that's doubled. There's nothing that's next to each other. So player 1 has won the game. And I'm recording all of the moves we did over here. We start off with 10 things in bin 1. And then our first one, we took 2 things and made something in the second one. The next move was we took 2 more things and made something in the second one. Then we combined something in we then split the 2 and so on and so on. When you look at this table, something should look a little strange. What looks strange about this table? So what looks strange about the table?
We got 9 zeros in F5 in the first 9 steps.
Well, it takes a while. So this is a good observation. It takes a while before we build up something that's large. That makes sense, right?
Yeah.
But if you just look at how this table is written, doesn't something look strange about how the table is written? Do you see how there's a gap over here?
Yeah.
That's a little strange as to why did I have a gap there. And the reason is what I did is I took a 1 and a 2 and I made a 3. I could have also taken the 2 and I could have split it. Okay?
Okay.
That's why I left the extra move. And if I do that, then the only move from this point onward is I have to take the 2 2s and make that into a 1. So the reason I left this here is player 1 wins this game in 9 moves because player 2 made a mistake here. If player 2 had made this move instead, then player 2 would have won the game in 10 moves. And there's a way to switch parity. Okay?
Okay.
And so I'm not going to go through the proof. I'll save this for the next lecture. All games end in finitely many moves. There's an upper bound for how long the game will take. There's a analysis of what the fastest game will be. There's a plot of the number of moves in a random game, and it looks Gaussian. And then player 2 has a winning strategy. So I'm not going to show the whole proof that player 2 has a winning strategy. I'm going to just show a little bit. And not for these Fibonacci game, for a related game. So this game is often called chomp. You have a rectangle of dots, and on your turn, you choose a dot. Let's say you choose this dot over here, okay? Then you eat all the dots from here up and all the dots from here to the right. And whoever eats last loses. If it was whoever eats last wins, where would you go to just win the game immediately? If whoever eats last wins. Is it possible to eat all the dots on your first turn?
Yeah.
Yeah, where do you go to eat all the dots on your first turn?
The bottom left.
Yeah, bottom left. So this is why we don't want whoever eats the last dot to win, because the game would be boring. Player one would just always go in the bottom left. I'm going to prove to you that player one always has a winning strategy. So there's two cases. Case one is player one has a winning strategy. So play it. Case two, player one doesn't have a winning strategy. We're going to see that there's a way for player one to switch roles and essentially become player two. This is similar to what we saw with the gap in the table, where player two can do a special move and basically just get to the same place, but force one more move to go on. So imagine player two has a winning strategy. So if player one goes here, there's some place for player two to go where player two would win the game. Let's say it's going all the way down over here and eating all these points, okay? So what that means is from this configuration on, player one is dead, player two has the winning strategy. Well, instead of having player two go in the upper right corner for their first move, where should player one have gone for their first move? They should just go over here. Because what we've just seen is if player one goes here and player two goes here, from this point onward, the person who goes next loses, right?
Yeah.
So if player one had just gone here, from that configuration, whoever goes next loses. So player one can ensure that they win. So I'm not going to go through the analysis. There's a way to set up and just, show that player two can force a win unless n equals 2. But it's now at the point where I can give you, some possible questions that we're going to be thinking about. So for the Fibonacci game, it would be wonderful if we could figure out what a winning strategy is. That's going to be extremely hard. But we could look at least at a deterministic game. Right now we have 2 moves, right?
Yeah.
Let's say we prioritize one move over the other. If we do that, can we figure out who's going to win and how long the game will take? So right now, we allow the players to play intelligently. What if we don't? Can we figure out who's going to win? So there's a lot of new material that we looked at today. And so it's probably not a bad idea that the other people weren't here and we'll be redoing some of this lecture so that you'll see it more than once. The more times you see it, the better. But what's nice is we haven't used anything calculus or higher. The challenge is going to be coming up with clever ways to think and look at things, to come up with clever quantities. Okay?
Okay. Okay.
Right. Any questions on today? Right. I'll get things posted. And then I'll talk to the other students And then we'll figure out when we're going to have our next session to really start talking about this again and then get to the point where you can start doing some new research, which would be exciting to start doing new things and not just listening to lectures. Sound good?
Yeah.
All right. So have a great rest of the evening.
You too.
All right. Take care.
You too.
Bye-bye.
Bye. Bye.